The secret of this is a chemical called polyvinyl alcohol. Now, I add just a little touch of water. Just gonna thin that down a little bit. Let's mix that up. So this is still obviously very watery. So next, I've got borax. Now, borax you'd actually find in the cleaning aisle. I'm gonna take a teaspoon, 5 milliliters, and then we're gonna add about a half a cup of water. The nice thing about slime, everyone's slime is a little bit different,
That's
right?
cool.
So now we got glue and water,
Yep.
borax and water.
Yep.
Also important, you wanna add your color now.
I'm going Jello Pool Red, Bob.
I love the Jello pool.
How much of that should I do?
Not too much.
Why?
It's gonna get on your hands. Your hands will be red for the rest of the video. So you wanna add it to your glue solution.
2 drops?
Yeah, let's start off 2.
I'm doing 3, don't tell Bob.
I heard that.
Whoa, you're
very
just
happy
looking
with that.
cool.
There are molecules in here and they're all loose. The borax is gonna bond all those together. You wanna just kind of experiment here. I'm gonna take maybe a teaspoon of this and you can see right away, look. Whoa.
Whoa, I'm doing 3?
Whatever you want.
I'm doing 4, don't tell Bob. Okay, but mine's like kind of goopy and runny.
That means that you still don't have a lot of bonds that have bonded, so
I
you
see.
add a little more of the
Okay,
borax.
I need more bonding.
This is a bonding activity. All right?
Whoa!
So if you let it sit for just a little bit of time, it makes a difference, right?
It does. And I like how it doesn't like get on your hands. It seems like it would be sticky, but it's not. What if I were to add color now?
It would be very hard to mix in, right? Because all those bonds are made. Give it a try. My hypothesis is that Mark's hands are going to be blue the rest of the video.
Uh-oh.
It might be blue the rest of the week. That is cool. It looks like a blue heart.
I get why slime is so popular.
Yeah.
And I'm gonna go wash my hands. For at-home science experiment number 3, we've got a fun one that's pretty simple. You just take a very clean plate and just put a nice little layer of water. Have you ever seen those water spiders that like glide on top of the water? The question is like, why does it float on the water? And why doesn't it just sink? We're gonna demonstrate that a little bit while I just pour a lot of pepper. It's on the surface. It's like one of those water spiders. Okay, then you just take a little bit of this blue stuff we like to call dish soap, put a wee bit of it on your finger like so, put it wherever you want. I'm gonna go right in the center. I'm a magician! I am a powerful wizard!
Pepperus Repellicus.
Whoa! You're a wizard, Bobby. What's happening here is dish soap has this special ability. It's called a surfactant. Surface tension is all the top layer of molecules in the water that are all joining arms. They're hanging together. Well, soap has this special ability to break those. As soon as you put soap, it rips that apart. And then almost like a rubber band, whoosh, they all go to the side. And this is why dish soap is so good at cleaning things. That's what I love about science. It's like magic, but it's actually real.
For experiment number 4, it's super easy. For this, you need clear glass and,
Whoa, whoa, Bob, whoa.
So this is seltzer water. Put a couple of raisins in here. And you see how immediately we got bubbles released, right? All right, now put some of these popcorn kernels
So
in.
far, Bob, I'm not gonna lie, this is kind of a boring.
It's kind of lame, I get it. Now, we have our
They
dancing
float, okay, they float.
popcorn. But then,
Wait, what? What is going on? So clearly the bubbles that nucleate on it from the carbon dioxide, that's like arm floaties that are gonna float you to the top. And then when it gets exposed to the air, the arm floaties get popped, they sink, they get more arm floaties, they go to the top.
so I figured let's add a variable. Let's do it something taller, right?
I think there's no way a corn kernel will go all the way to the bottom. Okay, I'm dumping all these in with
try
my
it.
blue hands, which someone didn't warn me about. Whoa, it's like a race to the top. Oh, okay, halfway, 3/4. Oh, go. Yeah, we hit the bottom. This is actually way more impressive in a tall cylinder. This is like a corn lava lamp. Get out of here, Bob.
I don't know if it's gonna work. I haven't tried this.
My hypothesis is that we're gonna get one that goes all the way down.
I don't think that.
Go, 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 go.
No.
No! Come on, you got this. Oh, go, go, go! No! We're getting closer, dude. We're getting close. Oh! Yeah! This is what experimentation in science looks and feels like, you guys. We're just thinking of these things on the fly. We're curious, we're asking questions, and we answer the questions. One question we had was which of the 3 containers would keep the corn moving the longest? And spoiler alert, it was the biggest one, which had the most liquid and therefore the most carbon dioxide or bubbles stored up in the water.
It's time for experiment number 5.
Bob, what is it?
Elephant's toothpaste.
You guessed it. And this is an experiment, just like all these, that you should definitely be doing with a parent or some kind of adult.
So let's start with our hydrogen peroxide.
We're gonna do 6 ounces.
I want you to get 3 tablespoons of warm water. There we go. To that, we're gonna add 1 tablespoon of the dry yeast.
Okay.
Now I'm gonna have you mix that up.
Okay. It's a little like hydrophobic, or meaning it doesn't mix well with water unless you really try.
So while we let that kind of mix a little
Okay,
bit,
okay.
I'm gonna go with a good squirt of our dish soap, maybe like a tablespoon. And finally, some color, classic red. Okay, so let's review. In here, we have our hydrogen peroxide, liquid soap, and we have our coloring.
Yes.
In here, we've got our yeast and warm
Warm
water.
water.
And then the last step is to mix them together. Now this is gonna act as a catalyst. It's gonna speed up a reaction that's already happening. There we go.
Okay, ready?
Ready. Pouring, 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 pouring.
Whoa, here it comes, Bob. Wow, that's so smooth. It looks delicious.
Very laminar.
Oh, that's so beautiful. Whenever I smell this,
Yeah.
it brings back so many fond memories. Yeah, nerd hug.
Spent a lot of time with this thing.
In fact, for the first elephant's toothpaste we did in the pool, we ran so many experiments trying to get the right combinations. And we just weren't getting as much volume as I wanted. So I called up Science Bob.
Told me exactly what you're doing,
Yeah.
and you weren't using warm water.
It's the
Warm
one
water?
variable we weren't considering. Why do you think warm water does the trick?
Formula for water is,
H2O.
right, so here's my little model.
So this is your H, and that's your 2 O's?
Right, so you got H2O.
Got it.
With hydrogen peroxide, it's H2O2. And so we add a catalyst, and a catalyst tears the extra O apart. It hooks up with one of the other O's that pulled apart, and now we've got oxygen and water.
This is why you want the right amount of catalyst to pull these off. If you don't have enough, maybe only half of the hydrogen peroxide molecules get ripped off like this, right?
So many experiments. All right, so that was the at-home version.
That's right.
Now this is 30%, which is why we have got our goggles on, we have got our gloves on.
And for the first time ever, I'll say why Bob pours this in. In the video description, we are putting the recipe for this version of elephant toothpaste. The trick is, you gotta do it with the science teacher, because only a science teacher will be able to get this 30% hydrogen peroxide. Plus, it is more dangerous, so,
Don't want to do it in your kitchen.
or your bedroom.
This up. Now, as my assistant, I need you to sand this Coke can. That's pretty good. Now we've sanded off all the labels. Ooh, we're gonna put this in. Instantly dissolving, that's crazy. Up next is aluminum can versus gallium. So the special thing about gallium is the fact that when it comes in contact with any aluminum surface, it will melt the aluminum. We can put the gallium on top. Why don't you spread it around? Safety touch. We'll need some time for the melting process to happen, so we'll check back on both aluminum can experiments later in the video. This next experiment needs to be done in the car. We'll just start with some Elmer's glue.
You're pouring glue in the car? Hafu, are you sure you're gonna be able to get that out?
We gotta trust science. Pour this into the cup, shake it up. Let's hope this works.
What if it goes into the engine?
Into the engine. All right, we have our beautiful slime. Now, this should clean our car. Clean the cup holder. Clean up some dust here. Clean up some dust. Now let's clean the steering wheel. Look at that, it's sucking everything up.
That's so gross.
Now we have a brand new car, completely cleaned with glue. This next experiment is the carbon sugar snake. This is our snake right here. It's just a mix of baking soda and sugar. What I need you to do is pour the rubbing alcohol. We want to pour this very concentrated. Ready? 1, 2, 3. Carbon sugar snake, come alive! So the sugar and the baking soda is now reacting with the fire. As the mixture burns, the carbon dioxide gas is getting trapped inside, which is making the sugar come alive.
What are you gonna name your monster, Hafu?
Big Willie. I'm sorry, my man. Cool thing about this, you can actually touch it after. It feels like a croissant.
Yeah.
You can like peel it open, spread it open. We basically made bread. All right, on to the next experiment. This next experiment only involves a simple egg. This is what happens when you drop an egg normally. It breaks, as expected. But when you put an egg and soak it in vinegar for 2 days, this is what happens. Our egg is now see-through. And what happened here is the acid in the vinegar has actually broken down the hard parts of the eggshell, which became these bubbles. This is a before and this is a after. Now, what's left intact is a membrane inside, so the egg is actually bouncy. Look at this.
That's so cool.
Let's make a bet.